We already saw this picture, right? However, I sense we didn't spend enough time on it. It is a fundamental illustration of deep nets. Whatever we do, we will come back to it, as it is simple yet so insightful. In this lesson, we'll spend extra time examining it thoroughly. The first layer you see is the input layer. Each circle represents a separate input. So, in this graph, we have 8 inputs. These inputs are the data we feed to train the model. In the TensorFlow framework, this is the placeholder for inputs. Remember the weather forecast example? Well, imagine it has 8 inputs. For instance, average temperature, highest temperature, lowest temperature, humidity, precipitation, atmospheric pressure, cloud cover, and visibility in the distance. Now remember, we combine these inputs linearly and then add nonlinearity. How can we do that? Well, linearity is easy. We'll just use the good old linear model. Its inputs are the x, and to combine them linearly, we need weights. In this example, the weights are an 8 by 9 matrix. 1 by 8 times 8 by 9 will give us an object with a shape of 1 by 9. Therefore, following this operation, we will get a vector of length 9, or a 1 by 9 matrix. This is exactly the number of hidden units we have in the first hidden layer. Okay, all these arrows will get us from the inputs to the first hidden layer. Each arrow represents the mathematical transformation of a certain value. So, a certain weight is applied, then a nonlinearity is added. Note that the nonlinearity doesn't change the shape of the expression, it only changes its linearity. Okay, so arrows represent weights and nonlinearities, right? But how many weights are there? The weights matrix was 8 by 9, so there are 72 weights. Well, guess what? We also have 72 arrows. 9 arrows go out of each input unit and into a hidden unit. Since we have 8 input units, this gives us 72 arrows. To be even more specific, each weight has 2 index numbers. The first one indicates the input it is referring to, while the second one indicates the hidden unit it is referring to. For example, weight 36 is applied to the third input and is involved in calculating the sixth hidden unit. In the same way, weights 16, 26, and so on until 86 all participate in computing the sixth hidden unit. They are linearly combined, and then nonlinearity is added in order to produce the sixth hidden unit. In the same way, we get each of the other hidden units. Alright, then what? Well, then we have the first hidden layer. Using the same logic, we can linearly combine the hidden units and apply a nonlinearity, right? Indeed. This time though, there are 9 input hidden units and 9 output hidden units. Therefore, the weights will be contained in a 9 by 9 matrix, and there will be 81 arrows. Finally, we apply nonlinearity, and we reach the second hidden layer. We can go on and on and on like this. We can add 100 hidden layers if we want. That's a question of how deep we want our deep net to be. And, of course, we will talk about that later in the course. Finally, we'll have the last hidden layer. When we apply the operation once again, we will reach the output layer. The output units depend on the number of outputs we would like to have. In this picture, there are 4. They may be the temperature, humidity, precipitation, and pressure for the next day. To reach this point, we will have a 9 by 4 weights matrix, which refers to 36 arrows or 36 weights, exactly what we expected. Alright, as before, our optimization goal is finding values for weight matrices that would allow us to convert inputs into correct outputs as best as we can. This time though, we are not using a single linear model, but a complex infrastructure with a much higher probability of delivering a meaningful result. Okay, I'm sure you know how powerful machine learning can be, right? At least that's how I felt when I was introduced to this picture. We are doing great, and we shouldn't stop here. There's plenty of work and learning ahead of us. After explaining the logic behind deep nets, there is a tiny detail we still must discuss. I bet you are wondering why we need those nonlinearities after each linear combination to create the next layer. Well, in the next lesson, we'll tackle this issue.